I'm interested in operant learning. And the operant learning experiments look something like the following. You have a participant, it can be human, it can be animal, and is presented with several options, often two options. She chooses one option, she is rewarded. She chooses an option again, rewarded again, chooses an option again and again, and every time she chooses an option, she is rewarded. And we are interested in the dynamics of the change of preference following choices and their outcome. Now, this is not a new topic, and the principles underlying operant learning have been formulated more than a century ago by Edward Thorndike, and are known as the law of effect. I will read it. Of several responses made to the same situation, those which are accompanied or closely followed by satisfaction to the animal will be more firmly connected with the situation, so that when it recurs, they will be more likely to recur. This is the basic idea behind operant learning, and in fact, this is not a new idea, and it was not a new idea also at the time of Thorndike. If we go back to the scientific literature of previous decades or millennia, we find in the Bible the idea that you can change behavior using negative reinforcers. And even the Bible probably wasn't the first to note this possibility of changing behavior. We find in earlier Assyrian scripts, we find same ideas. You can change behavior using negative reinforcers. So this is the basic idea underlying operant learning. Now, in the last decade, we moved away from a qualitative description of this phenomenon, of this learning, to more quantitative modeling. And I'll give you an example of quantitative modeling of such an operant learning task. So one common and popular model posits that in our brains we have an internal representation of the value or expected reward associated with each of these two alternatives, and it's denoted here by Q hat 1 and Q hat 2. And every time that we make a choice and we are rewarded, we update this internal representation of the value associated with this option according to the following equation. The change in the value is equal to learning rate, to some parameter which is known as the learning rate, times this delta, where delta is simply the difference between the reward that the subject received following his or her action and the internal representation. So this is one way, or one standard way, or one common way of modeling operant learning. And often we add to this model a model of choice, how choices are made given these internal representations. And one standard way and one popular way of doing it is to assert that the probability of choosing an action is a logistic function of these internal representations of the different actions, the values associated with the different actions, where beta is a parameter. So the more valuable an action is, or more precisely, the more valuable we think an action is, the more likely we are to choose it. But sometimes we also try the other option, and this beta parameter, sometimes referred to as the inverse of the temperature, determines the trade-off between exploration, trying options that don't seem that good, and exploitation, choosing the option that currently we think is the best option. So what do we gain from such a quantitative model relative to the earlier description of Thorndike? So what do we gain beyond these qualitative models? So one modest gain from quantitative models is it's a sophisticated tool for data analysis. And I will give a hypothetical example. So suppose you want to study the effect of consumption of different vegetables on our ability to learn. So we have one subject that tries the carrot and another one that tries a tomato. And in this simple two alternative false choice task as described before, and these are the choices made by this carrot eater, and these are the choices made by the tomato eater. So these are the trials, and every time that there is a circle here, this means that the subject chose the lesser good alternative, and every time that there's a circle here, you find that it implies that the subject chose the better alternative, and you see that in both cases, the participant learned to prefer the better option, and now we want to quantify this behavior. So one possibility is just to do an average, look at the average probability of choosing the better option as a function of time, drawing these two curves, and decide at a threshold that 80% of performance is a measure of learning, and then we find that this guy learned within 48 trials, and this one learned within 120 trials. So carrots are probably better for your learning abilities compared to tomatoes, but there is something arbitrary about 80%. So maybe we want to try 62%, and then we get slightly different numbers, although in this example, same result, but we can do something more sophisticated that takes into account all the trials and have a quantitative model and fit a learning parameter, in this case tau, and these are the fits, and so we can use our quantitative models as a sophisticated way of analyzing data without really claiming that this is how the brain works. But I'm interested in something that is more interesting, perhaps, more than just data analysis. And we do gain things that are beyond data analysis using quantitative models. So one thing is that quantitative models, unlike qualitative models, allow us to make quantitative predictions. And I will show one example. They may be useful for understanding the computational principles underlying the learning. And finally, they may help us to explain how the brain works. And I will briefly show examples for these three gains from quantitative models. I will start with quantitative predictions. So some years ago, I was interested in how in risk sensitivity in the framework of operant learning, and I studied behavior in a task in which participants had to choose between two buttons. One, unknown to the subject, one was considered a safe button. It always yielded the same reward. Whereas the other, a button, we called it a risky button because it yielded a high reward with some probability pH, and a low reward with a complementary probability. And we were interested in learning in this task. Unknown to the subjects, the reward associated with these two actions was on average very similar. Now, because the average reward is similar, the qualitative models that tell us, okay, subject will choose the alternative that yields a higher reward are not very useful. They don't make any predictions whether subject will go to this alternative or to this alternative. Together with Hanan Steingart, who was a student in my lab at the time, we used a version of the model that I previously described with two important changes to model behavior in the task. One is that we, rather than using the softmax function to relate the estimated values to probabilities of choice, we measured this function, and we found a way of explicitly directly measuring this function from the data, and this is how the function looks like, and we use this function rather than the softmax function. And another thing that turned out to be important is that we found that in this framework of the model, the first experience resets the initial conditions in this difference equation. And this results in a strong primacy effect that lasts for tens of trials, if not more. But more importantly, for our discussion, it allowed us to very accurately predict the extent that participants will choose the risky alternative based on the particular parameters of the experiment, namely the probability of reward and the magnitude of the high and probability of high reward in the risky alternative, and the magnitude of the reward associated with the three possible outcomes. And this is depicted here. So this is the result of our simulation, and this is the actual data. The X's are the test sets. I'm sorry, the circles are the training set, and the X is the test set. And we were able to accurately predict the behavior, the average behavior of participants in this task. And this is something that we were able to do because we had a quantitative model. And I guess that Thorndike would not have been able to do it using his qualitative formulation of the law of effect. The second thing that we gain as a community from a quantitative model is computational principles. So the model that I used and that I described previously to model behavior in this task is a particular example of a more complicated and more interesting learning rule that is known as Q-learning. And I'm not going to go into the details of the rule because they're not relevant, they're not essential for this talk. But what is interesting is that one can prove that learning in this, when you learn using Q-learning, in a family of problems that are known as Markov decision processes, you are bound under rather general conditions to converge to the solution to the Bellman optimality equation, which enables optimal control. So the idea is that if we see that participants in this task behave according to this, to these equations, we can infer that maybe what they actually do in the more general case is apply this algorithm. And the reason that they want to apply this algorithm is that it converges to the optimal solution. So now we understand in a deep way why people, or why participants, animals, people behave in the way that they behave. They do it because they want to solve the Bellman optimality equation. The third thing that we gain from quantitative models is that these quantitative models can help us explain what different parts of the brain are doing. And I will demonstrate it using an example. So going back to this algorithm, this Q-learning algorithm, there is a quantity, there is a variable here that is known as TD error, or temporal difference error. And in a very influential paper that was published more than 20 years ago by Peter Dayan, Wolfram Schultz, and Reed Montague, what they showed is that dopaminergic neurons in the VTA and substantia nigra, their activity, the firing rate seemed to reflect the temporal difference error in the particular task that they were in which the monkeys were trained. And following this understanding, or following this insight, people like Kenji Doya proposed that different parts of the brain now can be mapped to different aspects of this learning algorithm. For example, the cerebral cortex determines the state in the Markov decision process. Values are represented in the striatum, and these dopaminergic neurons, they can be considered as a teaching signal for the striatum, in which these values, these Q variables are learned. So this is one example. A similar example from later work. This is an algorithm that is known as actor critic. This is an algorithm that was developed in the framework of computer science, and this is a mapping of this algorithm to the brain. These are the dopaminergic neurons. This is the ventral striatum, dorsolateral striatum, hypothalamus, and so on. So if we have an understanding, if we can map behavior to these variables in the algorithm, now we can look for neurons that co-vary with these internal variables, and in principle, we can dissect the role of different neurons and different brain parts in the learning process. But the story is, I think, more complicated than that, and I think that there are serious challenges to this approach and to the use of quantitative models for operant learning, and perhaps the conclusions are more general in the cognitive sciences. So one challenge that I think has been to some extent overlooked is inconsistency of behavior. And I will give one example from a research project that I was involved in, and then discuss a more general case. So some years ago, together with Steve Lakiten and Thomas Bourreau, we were studying behavior and neural activity of monkeys in a two-armed bandit experiment, same experiment as described previously for humans. Every trial, the monkey could choose between one of two targets. One of the targets yielded a reward with a high probability, whereas the other target yielded a reward with a low probability, and monkey with time, with training, learned to prefer the better alternative. After 200 trials, end of the experiment, next day there are new targets, a new rule to learn, but the same principle. And what I present here is the performance of the monkey as a function of trial number. So initially the monkey is more or less a chance level, but with time the monkey learns to prefer the more rewarding alternative. And so this could be viewed as standard operant learning, and perhaps could be modeled using the model that I described previously. But if we look more carefully at the behavior in the last 20 trials, what we find is substantial heterogeneity between days. So this histogram depicts the fraction of trials within the last 20 trials of the experiment in which the monkey chose the more rewarding alternative. So in some days, the monkey was perfect. All the trials in the last 20 trials were those targets, all the choices that the monkey made in the last 20 trials were those of the alternative associated with a higher reward. And there were other days where the monkey was close to optimal. But there were many days in which, even after 200 trials, the monkey was more or less a chance. And even some days in which the monkey learned to prefer the less rewarding alternative. And looking more carefully at the behavior on these trials, what we found that in many cases, and I'm not going to exactly describe this, the details of the analysis, in many cases, the monkey learned to prefer a side and not a target, despite the fact that the side had nothing to do with the amount of reward that it received. And from the experimental point of view, there was no difference between these days or these days or these days. There was nothing, at least to the best of our knowledge, in the experimental design that could predict whether eventually the monkey will learn or will not learn the task. Now, if behavior is inconsistent, can we expect a quantitative model to explain it? We first need to figure out what's going on behaviorally. But this is one example, one paper. There's another story which I find a bit troubling, and this has to do with a phenomenon that is known as probability matching. So there's a long history in the cognitive sciences, starting as early as the 1930s, in which participants, initially humans, but later also animals, are presented with the following task. There is a source of light, and every trial, the source of light can be either on or off. Generating a binary sequences of ones and zeros. And the task of the participants is to predict what would happen in the next trial based on the history. Now, it is generally believed that behavior in this task follows something that is known as probability matching. So the probability that the participant will predict that the next trial would be on relative to the probability that it will predict that the next trial it will be off is approximately equal to the ratio of the true probabilities. So let me give you an example. Let's say that the probability of on is 70%. In 70% of the trials, participants will predict that the light would turn on. Now this is weird. This is weird. Why? Because if a participant figures out that in 70% of the trials a light would turn on, then the best policy would be to always predict that it will turn on, and then the participant will be correct in 70% of the trials. If the participant follows probability matching, then in 70% of the trials it will be correct with probability of 70%, and in 30% of the trials it will be correct with probability of 30%. Doing the math, it turns out that participants will be correct with a probability of 56% rather than being correct with a probability of 70%. And this bothered especially economists, and this is an example as early as 1958, citing Ken Arrow that later received the Nobel Prize in Economics, and he's saying the following thing. The remarkable thing about this is that the asymptotic behavior of the individual, even after an indefinitely large amount of learning, is not the optimal behavior. The individual does not, in fact, at any point, even in a limit, reach the optimal behavior. And if you are an economist that believes, at least this is what economists believed in the 1960s, that choices are in some sense optimal, this is troubling. 40 years later, more than 40 years later, economists still are interested in this problem. This is a paper, this is a review paper by Nir Vulkan published in 2000. And going back, trying to explain this puzzle, and he's saying probability matching is not robust, and some people do end up maximizing their expected utility. He said that asymptotic behavior depends on experience, size, and direction of payment, age, and the observability of the random device. The rate of learning depends on experience, size of payment, and so on and so forth. So basically what he says is that the question of probability matching is open because sometimes people do probability matching and sometimes they don't do probability matching. Sometimes they maximize and sometimes they don't maximize. There are many, many, many factors that determine whether they will maximize or they will not maximize, including things like age, size and direction of payment, things that we will not commonly, that will not be part of our models. Now, what I find remarkable about it is that 90 years or so after starting these experiments, we still don't know how people behave in these tasks. Different labs, different conditions result in very different behaviors. This is remarkable. How are we going to model it using a quantitative model? Now, I have some ideas about why this is the case, and I think that small changes to the experimental design result in a very different set of hypotheses that the participants are willing to test in the learning process, and this is what underlies the very different behaviors that are observed in this type of experiment, and why small changes to the experimental design result in large changes to behavior. But if behavior is inconsistent, even in the simplest experiments, what hope do we have to quantitatively model it, successfully model it? Second problem is that we don't have one model, we have many models, and the models are inconsistent with each other. And I'll give you just a small number of examples relating to this simple task. So there's a family of models that are based on Q-learning, the original model that I described in the beginning of my talk. This is by far the most popular way of modeling behavior. These are just examples of people who use this approach. There is another family of models that does not have an explicit representation of value, that are based explicitly or implicitly on the idea of a direct policy gradient. And yet there is a third family of models, a large family of models, starting with simple models like win, stay, lose, switch, moving to regression models and other more sophisticated models that I could call phenomenological models, in the sense that they are not based on any specific reinforcement learning algorithms. Now, one would have expected with this large zoo of models that people would be very, I mean, maybe we should expect wars in the community of modelers between people who believe in Q-learning and people who take this approach. But it turns out that often you find the same researcher publishing papers in similar tasks that are associated with models that are very different from each other. This is just one infamous example of contributions to these very different families of models. Perhaps even worse is that you find that the same data set is used to justify very different models. And this is a science paper, and this is a Nature Communications paper, same data set. I can freely fight it because I'm on this paper, so I feel that I have the right to go against this use of the same data set for different models. So which of these models is the right one out of these and the many others, and how do we compare models? Now, we have a way of doing it, or standard way of doing it is based on a log likelihood with correction for complexity, but I'm not sure that we are successful given the large number of these very different models. A third issue is the difficulty of relating these models to neural activity. And I will give one example from a work that I was involved in. And about 15 years ago, a very interesting paper by the lab of Kimura argued that the neurons in the striatum code for the value of the different actions, following the algorithm that I showed you previously. So these are the action values. And this was the first paper, a science paper, and it was followed by approximately 20 other papers that did similar experiments and came to the same conclusion, papers in Neuron, PNAS, and Nature Neuroscience, and so on. Together with a student in my lab, Lotem, we dug deeper into the analysis that was used in these papers, and what we found, to our dismay, that this result is based on a statistical confound, which I don't have time to explain. It is all published. So all these papers share the statistical confound, and all the other papers, the black ones, actually could not distinguish between this particular claim that striatal neurons encode action values and other decision variables. And in this paper, you find we repeated the analysis of each and every paper in these, each and every red paper. So there's no evidence, no real evidence for representation of action values in the striatum. But this was not the bad news. The really bad news is that it turns out that it is extremely difficult, if not impossible, to use this model to identify neurons that really encode action values. And the reason is the following. So neurons that encode action values are neurons that encode this internal representation. Now, if a neuron, so how do you do it? You look for neurons whose activity co-varies with this variable. But any neuron whose activity co-varies with this variable, you expect that its activity will also co-vary with the probability of choice, because the probability of choice is a monotonic function of this action value. Now, if a neuron is correlated with this preference, it will look as if it is correlated with Q1. Now you could say, okay, I'm looking for neurons that are correlated specifically with Q1 and not Q2, but the fact that a neuron is not correlated, is not significantly correlated with a variable, does not mean that it is not correlated with this variable. And it turns out that if you have a little bit of noise, then a neuron that is correlated with this will look as if it is correlated with this. So it is very difficult to go from these models back to the brain and make arguments about computation taking place in individual neurons. Okay, so this is where we stand. We have qualitative understanding of operant learning, starting with the law of effect, but we do have other things, like we know that there's primacy and recency in this behavior, Pavlovian bias, all kinds of things that we already know that are associated with operant learning. We have quantitative models. Many of them are based on algorithms that were developed in the field of computer science. But we have problems, inconsistencies in behavior. It's not that we have one model or two models or three models. We have many, many, many models, and we don't really know how to choose which one is the right one. And I think that the amount of insight that we have from these models to neural activity is smaller than is claimed in the literature. So this is kind of disappointing for someone like me that is interested in quantitative modeling of operant learning. So I try to see what's going on out. Maybe, is the grass in other fields of science and technology, is it greener? What do they have that we don't? How come that their models are good and our models are not that good? I'll try to answer this question. This is a figure that I took from, I took the data from Wikipedia. perhaps the most exciting figure in my talk. This is it depicts the tallest freestanding structure as a function of time, the tallest in the world. So this is about 5,000 years ago, and this is today. And so I'll give you a second to guess what this one is. This is the Great Pyramid of Giza. This was the tallest building in the world for millennia until this building was erected. This is the Lincoln Cathedral. It was the tallest building for about 250 years until, well, nothing new was built once the towers fell down and it ceased to be the tallest building. But all these buildings are less than 200 meters until the Eiffel Tower, that almost doubled the height of the tallest building at the end of the 19th century. And from there on, we have the skyscrapers. Today, the tallest building is Burj Khalifa. And in Saudi Arabia, they are building the Jeddah Tower that is planned to reach 1 kilometer. This is a logarithmic scale. Note that this is a logarithmic scale. And I think it's very clear that something happened here. There's before the Eiffel Tower and after the Eiffel Tower. And many things contributed to this revolution. But I'd like to argue that accurate quantitative modeling was part of it. This was part of the success of structural and civil engineering and part of this revolution. This is just an example of a model of wind pressure. And today we have accurate models of many things, and we use these models when constructing buildings and bridges. We cannot reach these heights without quantitative models. And the success of engineering is a testimony of the accuracy and useful of the underlying quantitative models. So can we do something similar in the field of operant learning? Can we use quantitative models to engineer behavior? And similar to the way that we use quantitative models in other fields of science to engineer other things. Now, we already know that we can use the qualitative models to bias behavior. Any salesman, politician, parent knows that it can bias behavior by understanding how humans behave in a qualitative way. Richard Taylor, that received the Nobel Prize 3 years ago, in his best-selling book Nudge, coined the term choice architecture. The idea is that you can use qualitative psychological principles to change preference without changing the objective value of the different options. So this is an idea of how what a choice architect may do. So the idea is that by changing the order of different food items, one can indeed change the preference of the eater, maybe biasing him or her to eat healthier food. The question that we ask ourselves is similar to the revolution when people moved in the field of structural and civil engineering, when they moved from qualitative models to quantitative models. Are we in the verge, or can we contribute to move from choice architecture to choice engineering, or perhaps a different way of looking at it, use choice engineering or the success or failure of choice engineering as a way of testing our quantitative models? To do that, we were thinking what can be an engineering challenge in the framework of operant learning. So for example, let's say that our goal is to construct a reward schedule, a sequence of rewards associated with action that maximizes the number of times that a participant would choose the left-hand side alternative using binary rewards. Now this is trivial. Now, if every time that a participant would choose left, she will be rewarded, whereas every time she will choose right, she will not be rewarded, we believe that this is the most effective way of biasing the participant into choosing left. Let's try something that is perhaps more demanding. The same thing, choose left as often as possible, but with a reward schedule that is constrained. So 100 tries. You cannot give 100 rewards, you can only give 50 rewards, but you have to associate half of the rewards with the left-hand side choice and half of the rewards with the right-hand side choice. What would you do? Turns out that about 10 to the 46 different reward schedule, but if you understand how people choose, if you have a good quantitative model, you can choose the best reward schedule out of them. So can we really do it? So before moving to quantitative models, what would you do if you were a choice architect? Now, one thing that you could do is to say the following. Well, we know that there is primacy. So we can associate all the rewards on the left-hand side in the beginning to associate the 25 rewards to the left-hand side. So the participant will learn to prefer the left-hand side. And then he or she will remain choosing the left-hand side. And maybe at the end, he or she will shift to the right-hand side, but there are only 25 trials left. So this perhaps is the optimal way of biasing participants. But if you have a particular quantitative model in mind, you can in principle test many of these different 10 to the 46 different reward schedules and find one that is more effective. If you have a different quantitative model of behavior in mind, maybe you will find a different model, a different reward schedule. And now we can test these different reward schedules on humans and see which ones would yield which one will be more effective in biasing choice. So this is in a simulation. We took a model of an agent that learns using the Q-learning algorithm. We used a naive reward schedule. We used a reward schedule that was optimized for this quantitative model. We used a reward schedule that was optimized for a different reward schedule. And we found that indeed, as expected, if you have an accurate model of choice, you can be more effective in designing a reward schedule, in engineering a reward schedule. We took this idea and asked the community to propose reward schedules based on their preferred model of choice, based on their quantitative model or qualitative model of operant learning. And today, this is the first time that I'm presenting the results of this competition. So these are 12 schedules that we tested. So what you see here is the fraction of bias, to what extent were the different schedules capable of biasing choice in one of the direction, in the preferred direction. These are the different reward schedules. And each of these bars is based on a large number of human participants that were tested on these different reward schedules. So for example, if we look at this specific reward schedule, then this is a distribution of biases over the different participants that were tested on this schedule. In this case, more than 500 participants. And you see that not all of them were biased. Some of them prefer to choose the other side, but most of them, all those to the right of the 50%, were biased to the right. And there is a cutoff here because participants that chose one of the options more than 95% of the trials were discarded from our analysis. Okay, I showed you earlier that we have a fantastic model that is based on Q-learning that can predict behavior in the safe, risky, risky task. This is a success of our model. So we use this particular model to engineer a reward schedule. Were we successful? Not really. This model failed when trying to engineer behavior. But one has to bear in mind that these were tested on humans in a lab, and this was done online, and the rewards were different. So perhaps we need to use different parameters, still keep this model, but use different parameters. We had a test set that allowed us to fit the parameters to this model. So we optimize the schedule for optimal parameters using the Q-learning model. Complete failure. These two are not significant, but certainly they don't represent a success of reward engineering. What can we say about the successful ones? These three most successful schedules. So the first one was a schedule that we designed using something that I would call the simulated annealing. Basically, we tried one schedule and we looked how people behave, and then we changed parameters in the schedule and tried again, and we changed and tried again. Using trial and error, we optimized this schedule, not based on any first principles, neither qualitative nor quantitative. What it does, it provides a lower bound to the extent to which different schedules can bias behavior. The second best schedule was a schedule that was based on engineering, but on one of the phenomenological models, a model that is called the KT model that I will describe in a second. And the model, the schedule that came third was a choice architect that thought very hard about how people behave in this task and came up with this particular reward schedule. I will not go into the details of the KT model because I'm running out of time, but basically it's a phenomenological model that is based on four variables. One is the idea that you want to choose an option if you think that things are improving. In that side, sometimes you want to explore, sometimes you want to continue the way that you chose previously, and sometimes you want to look at what happened in the past, what was and use it to choose your actions. It's kind of complicated, and I'm not going into the details. But this was the model that won this. A road schedule that was based on this complicated model won in the competition. So to summarize the thing that I said, in the field of quantitative modeling of operant learning, I think that we have serious issues that we as a community must address. First and foremost, these inconsistencies in behavior. The fact that we have too many quantitative models and it's not clear how to choose between them. And we are not careful enough when we try to relate these models to neural activity. I propose the idea of engineering as an approach to comparing models in operant learning, and reinforcement learning, but perhaps more generally in cognitive sciences, because it goes beyond the fitting of a model to a particular data set. Surprising to me, the engineered the winning model was a model that was a phenomenological model that was not derived from reinforcement learning and any optimization consideration. This was just based on many experiments and a lot of thinking of psychologists. This is a model that won the competition without any parameter tuning, and its level of performance was comparable to that of a choice architect. So there is something in this model, and perhaps in a more complicated setting, it would have been able to do much better than choice architect. But the weakness of this model, it's not clear how to generalize it to more sophisticated tasks, maybe three, not two alternative, but three alternative. We all know that all models are wrong, but some are useful. We like to cite this to repeat this statement. And I think that we should remember that models are wrong and be more careful when relating them to behavior and to brain activity. One last point, going back to this revolution in engineering, I think that it's a question that we as a community should ask ourselves is whether we are here, whether we are on the verge of a revolution in which we will be able to engineer behavior using quantitative models. Perhaps, I'm not sure, I don't know. It's not clear that we want to be here. There are ethical issues associated with choice engineering. There are also ethical issues associated with choice architecture. But if choice engineering will turn out to be much more effective than choice architecture, then maybe we are maybe this is dangerous for us as a society. Finally, I want to thank my group. This is my group, a photo taken in front of LSEC, a spectacular building just before the corona. And the two students that contributed to this work was Lotem and Ohad. Ohad is now a postdoctoral fellow in Yale. And thank you for coming and listening.